In this video, we're going to be talking about molecular polarity. A couple reminders about bond polarity, which we have covered in a previous unit. We want to remember that when we talk about a polar bond, in particular a polar covalent bond, we said that the difference between the electronegativity was between 0.7 and 1.7, and we would say that bond was polar. When we say a bond is polar, what we mean is that there is an uneven distribution of charge, sometimes called a dipole. If you think of the word dipole, it has the word di, or the prefix di, which means two, and pole, which means opposite ends. So what we have is we have two opposite ends. It contains a negatively charged region and a positively charged region. The higher electronegative atom, which we defined as the strong nonmetal, will contain a partial positive charge because it is pulling the bonding electrons towards itself. On the other end, we have a lower electronegative atom. We call this the weak nonmetal, and it will contain a partial positive charge because the electrons are being pulled away from it. Now, there were two different ways that we could represent this bond polarity. One of the ways that we can represent it is by putting what you see on the screen, which is a lowercase delta symbol. This lowercase delta symbol represents the idea of partial. So we can put a partial negative on the strong nonmetal, and then we can put the partial positive on the weak nonmetal. That would look something like this. If we had a bond between a chlorine and a carbon atom, chlorine is our strong nonmetal, which is going to get the partial negative charge, while carbon is the weak nonmetal and will get the partial positive charge. The other way that we can show dipoles or this polarity is to show the dipoles using an arrow. We want to remember that this arrow does have a tail and it points towards the more electronegative atom. You could also think of it as the arrow is being pointed towards the way that the electrons are being pulled. Right here, at the bottom or at the other end of the arrowhead, this is the tail that I'm talking about. This tail looks like it's almost like a positive, and it is going to be on the atom that has a partial positive sign, and we are showing that the electrons are being pulled towards chlorine. Now, we're going to be applying what we know about bond polarity to molecular polarity. This occurs when there's an uneven distribution of charge on the molecule. This results in a positive region of the molecule and a negative region of the molecule. This is due to polar bonds not being canceled out due to the molecular geometry. So, for a molecule to be polar, it must contain two things. It first must contain a polar bond. Second, it must have a geometry such that the polar bonds do not cancel out. So let's take a look at what that might look like. I have on the screen a couple helpful steps when we are trying to figure out if a molecule is polar or nonpolar. One of the things that you should always start with is a Lewis dot structure. Take a minute, and when you draw the Lewis dot structure, make sure to adjust the drawing to show some of the geometry. We want to remember that the geometry is actually a really important part of this. Then we want to identify if there are any polar bonds within the molecule. If there are no polar bonds, we are going to say that the molecule is nonpolar, and we get to go ahead and stop there. However, if there are polar bonds within the molecule, we want to draw the dipoles and then identify if the dipoles add together or if they cancel each other out. Is there a geometry such that they are not fully canceled out? If the dipoles cancel out, the molecule is overall nonpolar. But if the dipoles add together, we then can say that the molecule is polar. So let's take a look at some examples. So what if we were asked to look at the molecule of methane, CH4? Is this molecule polar or nonpolar? Again, the first thing that we want to do is we want to draw the Lewis dot structure of the molecule and include a little bit of that geometry. So here's would be our Lewis dot structure of the molecule. This geometry is tetrahedral. We see that we have some hydrogens coming out of the screen and some going back into the screen. But when we ask ourselves the second question, or if we go to step number 2, and we see, are there any polar bonds within the molecule? What we want to be looking at is the bond that holds the carbon and the hydrogen together. Looking at that, what we see is that the carbon-hydrogen bond is actually nonpolar. Those are both considered weak nonmetals. So because they're both nonpolar, that means that this molecule must be nonpolar. Let's look at another one. What about carbon dioxide? Is carbon dioxide polar or nonpolar? Well, let's go ahead and draw our Lewis dot structure. Here's our Lewis dot structure. We have carbon, and it is bonded to or double bonded to each oxygen. So the first question that we want to ask ourselves then is, are there any polar bonds within the molecule? And if we look at the bonds that are represented within this molecule, that carbon-oxygen double bond, we would say that yes, there are polar bonds within this molecule. It is the carbon-oxygen bond which is polar. Oxygen is a strong nonmetal, and the electrons are being pulled towards oxygen away from carbon. So we can draw our dipoles on that molecule. Then what we want to do is we want to ask ourselves, do these dipoles cancel out? And if you look at the geometry and you kind of imagine that these are vectors, if you've taken physics before, or kind of imagine that if you were to overlap these two arrows, they would actually cancel out. So these dipoles are actually equal in strength and opposite in direction, and they cancel each other out. This molecule is nonpolar. Now, what about our water molecule? Is water polar or nonpolar? Okay, same steps that we were doing with the other two problems. Here's my Lewis dot structure. Notice I'm not showing the lone pair of electrons on oxygen. That's really not as important when we're looking at identifying if the molecule is polar or not. But as you can see, we have represented some of the geometry within this molecule. This molecule is bent. So then we want to ask ourselves, are there any polar bonds within the molecule? So we're looking at that oxygen-hydrogen bond. What we see with that oxygen-hydrogen bond is that yes, indeed, that hydrogen bonded to the oxygen is polar. So we're going to go ahead and we're going to draw our dipoles pointing towards the oxygen. Then we want to ask ourselves, do these dipoles cancel out? And if you were to take these two dipoles and you were to put them on top of each other, they wouldn't actually cancel out. They would kind of just add together. So when they add together, we get this arrow that you see in green on your screen, which is the overall molecular dipole of the molecule. And what we see is that these do not actually cancel out, they add together. As you can see, we have a positive region on the molecule and we have a negative region on the molecule. The oxygen side of the molecule carries a partial positive, while the hydrogen side of the molecule carries a partial positive. I think I said partial negative on oxygen, partial positive on hydrogen. So this is actually a really important molecule to know, and you should be really comfortable being able to draw this molecule and identify the positive and negative regions of it.